All right, let's continue our conversation about acids and bases. And we were talking about how to identify the stronger base. And so we did that by using the pKa table, which is a little bit surprising because the pKa table tells us things about acids. So how are we going to use the pKa table to find out something about a base? Well, it turns out that we are going to turn our bases into acids, and that's kind of what we did last time. So let's do an example. This type of problem shows up on exams all the time. It says, example, identify the stronger base in each pair. So I'm going to give you like a couple molecules and you may have to choose the strongest base. So let's do an example of that just to see. This is kind of a review from the last lecture. All right, so say for example we had this molecule and we want to compare it to this molecule here. Okay, so on the left we have a deprotonated alkyne and on the right we have a deprotonated amine. To determine who is the stronger base, we need to look at the pKa of the conjugate acid of each of these. Like I said, we need to pretend that these bases are going to become acids and then look at their pKa values. So what we need to do is, if these are bases, they're going to gain a proton. They're going to gain a hydrogen atom. And so what we're going to do is we're going to replace the negative charge with an H. So in other words, this deprotonated alkyne is going to become just an alkyne. H is going to replace the negative charge in the lone pair. And similarly here, we're going to replace that negative charge with a proton because both of these things are acting as bases. They're both going to be gaining a proton. And when something gains a proton, it loses its negative charge because what's the charge of a proton? Plus. So the plus and the minus sort of destroy each other. And so then you're left with these molecules here that are neutral. Now we can look at the pKa table, and we find the pKa of an alkyne is 25, and the pKa of an amine is 38. That's what we've created now. So the pKa of our alkyne is 25, and the pKa of our amine is 38. Now, whoever has the higher pKa is going to be our stronger base. So in other words, since the amine has a pKa of 38, versus 25 for the alkyne, the deprotonated amine is the stronger base. Let's do another one just for practice here. Let's take this deprotonated thiol versus a deprotonated alcohol. Lovely. Okay, we'll protonate both of these in our head. So we'll be adding an H to the sulfur and adding an H to the oxygen. We look at our pKa table. I'm not even going to write down the conjugate acids. You can kind of envision what they will look like in your head. Look at the pKa table and we'll find that if we add an H to our oxygen, we'll get an alcohol. And if we add an H to our sulfur, we'll get a thiol. The thiol is 13, the alcohol is 16. So we can go back here. So 13 for our thiol, 16 for our alcohol, and now that means that who's got the higher pKa? The alcohol does. So that means this is our stronger base. Let's do one more. Okay, this one's very similar to the previous one. The only difference here is that they don't have a negative charge. They're already neutral. They're already protonated. So be careful. We still need to protonate them. We still need to treat these guys like as if they are bases. So they still need to gain one more proton. Let me just draw in the lone pairs. So where are these guys going to gain a proton? There's no negative charge. So the proton's not going to be electronically attracted to either of these. However, there are lone pairs, and so the proton will go towards the lone pairs and get added there. So that the conjugate acids of these guys, I'll go ahead and draw these out, will look like this. SH, and then there's going to be another H added, and now we need to add a formal positive charge for that sulfur. And similarly, the oxygen is going to grab an extra H, formal positive charge for the oxygen there. Now we look at our pKa tables for these conjugate acids, and so we're looking not for thiol, but protonated thiol, and we see its pKa is -7. Okay. So this will be -7. And then we look now for protonated alcohol. We see that's pKa is -2. Okay, so who's got the higher pKa of the conjugate acid? Well, -2 is a greater number than -7. So that means that our alcohol is more basic than our thiol. Okay, so that is how we identify the stronger base. Next topic I want to bring up is using pKa to calculate something called KEQ. You did this in Chem 101, I think, but let's just refresh that for a second. So using pKa to calculate KEQ. Let's take a look at an example acid-base reaction. Now let's say we have our deprotonated alkyne. And let's add that deprotonated alkyne to water. And there's going to be an acid-base reaction. Remember, all acid-base reactions are technically reversible. There's those equilibrium arrows. If you just draw a regular arrow, I won't take off points. I never take off points for forgetting to draw the double arrow, so don't worry too much about that. And then if we do this reaction, let's say that this is going to be our base and water is going to be our acid. So our base is going to gain a proton and become the alkyne, and our H2O is going to lose a proton since it's the acid, and it's going to become hydroxide. Okay, now let's identify the players in this reaction. So our deprotonated alkyne is our base. Water is acting as our acid since it's giving up a proton. The base becomes the conjugate acid, and the acid becomes the conjugate base. So you've done that before in general chemistry. So what we can do is calculate something called KEQ. KEQ is going to allow us to determine how favorable this reaction is. Does the equilibrium lie on the left side, or does the equilibrium lie on the right side? How likely is this reaction to proceed in a forward direction? KEQ tells us that. It's the equilibrium constant. To calculate KEQ, it is so easy. You simply look up the pKa's of the conjugate acid and the acid. So water, it has a pKa on our pKa table of 16. So we'll just go ahead and write that down here. So water has a pKa of 16. And then we'll also look up the pKa of our conjugate acid. Our conjugate acid is an alkyne. It has a pKa of 25. We just saw that on the pKa table just on the top of this page. All right. Now we can just simply calculate KEQ. You're going to laugh how easy this is. So KEQ equals 10 to the power of the pKa of conjugate acid minus pKa of acid. So if we do that math, we get 10 to the power of 25 minus 16, which is equal to 10 to the 9. Now, is that easy or what? Now, what does that tell us? Well, if KEQ is greater than 1, the reaction favors products. In this case, that is true. So KEQ is 10 to the 9. That's much, much bigger than 1. That's a billion. So the reaction favors the products a billion to 1. That's what it tells us. So if you did this reaction, there would be a billion times more of this than this. Now, if KEQ equals exactly 1, well, that is going to be an equal ratio, meaning that, and this is pretty rare, meaning that neither side of the reaction is favored and it will lie 50-50. And then KEQ is never negative, but if KEQ is less than 1, for example, like 10 to the minus 9, then that would mean that the reaction favors starting materials. So you can see the pKa table is very, 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 very powerful. Was that enough varies? Normally in this class, I would make you memorize the pKa table, but because we're in the online class right now, I will allow you to use the pKa table during the exam. So you're welcome. The pKa table, now we've seen it. You can use it to determine acid strength. The lower the pKa, the stronger the acid. You can use the pKa table to determine base strength. Now, not directly, but if I gave you two substances that are bases, you can find their conjugate acids and look up their pKa's, and that will tell you information about the original substance's base strength. And now we can see we can use pKa to calculate the KEQ. The KEQ will tell us if you mix an acid and a base, how likely is that reaction to occur and go on to products, or will the reaction fail to occur, it will stay at starting materials, or will the reaction be in a perfect equilibrium 50-50? So that's 3 things that the pKa table can tell you. Now, sometimes we'd like to compare acid strength without using the pKa table, and we can do that as well. So that's going to lead us to our next topic, which is called the REO method. Well, I won't say comparing pKa, I'll say comparing acidity without the pKa table. And we'll call this the REO method. REO is an acronym that's going to help you. And the whole concept behind this is that the weaker the conjugate base, the stronger the acid. So weaker the conjugate base, in other words, the more stable it is, that's going to equal a stronger corresponding acid. So that little piece of information may not make sense, but when we do some examples, it'll start to become more clear. Before I show you some examples, let me just tell you what REO stands for. The A stands for atom. The R stands for resonance. I stands for induction. And O stands for orbital. And the nice thing about REO is that these are the factors in order of importance. So atom is the most important factor, then resonance, then induction, then orbital. We'll talk about how to use these factors to rank acidity without the pKa table. So kind of the best analogy I could think of is sort of like a relationship doctor. So I want you all to pretend you're relationship doctors and you get paid to do relationship coaching. Okay? So let's take 2 couples. Couple number 1 will indicate like this. And this couple in our analogy is an acid. So just like a couple, there's 2 people involved. One of the partners is a proton, and the other partner is, we'll just call it A. So a proton attached to A, that's our couple. Now, some couples are very codependent on each other, meaning that together they're perfectly happy, but if they like spend some time apart, or one goes to work and the other doesn't call them, they start getting really, really, really upset. They can't live without the other partner. They're desperate to be with the other partner. In a way, this is kind of an unhealthy relationship. They love each other very much, but they're also very codependent on each other. So what will happen if, for example, H goes on a business trip? So let's say minus H plus. In other words, just like an acid is going to give up its proton, H is going to go on a business trip. And it's going to leave behind the conjugate base, which is one of the partners on their own. And we'll show that as A minus. Now, A minus, if this is a codependent relationship, is now going to be very unstable because she's without her partner. Now let's take a look at another couple, HB. HB looks just like HA, very happy couple, but they are not codependent. So when H plus goes on a business trip, B is not jealous, B is not paranoid, B doesn't think H is going to be cheating or anything like that. So B is perfectly stable on her own, okay? So imagine you're the relationship doctor here, and you're trying to figure out which one of these relationships is the most healthy. This would be an analogy of a chemist trying to determine which one of these substances is a stronger acid. That's sort of the job of the chemist compared to the job of the relationship expert. Okay, now one thing you could do as a relationship expert, and maybe this would be your strategy, is to look at the couples and interview them. That would be like looking at the pKa table to determine acidity. You would interview each couple, you would look up in your chart what their responses mean, and that would be like looking up on the pKa table, and you could say, okay, this couple is more stable than the other based on this evidence. However, one problem with that is that together, the couples, they may both seem happy because even the codependent couple they're happy when they're together. A far better way, I think a far cleverer way for you to do your relationship doctoring is to look at the partners on their own after they've been split up and see how they are and see how stable they are. And that would give us clues about how strong their relationship is when they're together. So that is what we're going to be doing here. We are going to be comparing the stability of the conjugate bases. If the conjugate base is very, very, very stable, that means that the acid is very, very, very strong. If the conjugate base is very, very, very unstable, that means the acid is going to be very, very, very weak. Okay? And you can kind of think of it like this. Imagine A is really unstable. What's going to happen when H tries to leave? No, 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 come back, come back. I need you to come back. I need you. And so it's not going to dissociate. HA is not going to be able to give up its proton easily because A is going to want to rip it back. Versus a very stable relationship, the H is much more likely to be donated away as an acid because the conjugate base doesn't care so much. It's like, oh, you want to go? Fine, go. We're stable. We're happy together anyway. So you can go. So there's not likely for the conjugate base to rip the proton back. So in that case, the equilibrium for a stable conjugate base lies far more to the right, making it a stronger acid. Because remember, the stronger acids give up their H's much more readily. Okay, that's enough of the analogy. I think you guys get that by now. And so let's talk about REO, and let's start with number 1, which is atom effect. Okay, atom effect. So the atom effect says the same row, if you're in the same row element, more electronegative atoms are more acidic. Let's do an example to compare. Carbon versus oxygen. So let's take a look at two potential acids and use the REO method to determine which one's more acidic. So let's take butane. So there's butane. And if we treat that with a base, in other words, the butane's going to act as an acid and we're going to add some base to it. We're going to deprotonate the butane and we're going to get the butyl anion, which looks like this. Now let's take propanol, treat that with the base. If we remove the proton from propanol, we're going to remove the H on oxygen and we'll end up with the ethoxide anion, or propoxide anion. Okay, now we can use REO to determine which one of these is more stable. And the rule says for A, atom, if you have a same row element, which carbon and oxygen are in the same row, the more electronegative atom is more acidic. And the reason for that is that the more electronegative atom is more stable with a negative charge. So here we have the more electronegative oxygen atom better able to stabilize the negative charge. So what that means is that this guy is more stable. So because the conjugate base from deprotonating oxygen is more stable than deprotonating carbon, that means that the propanol that we started with is more acidic. Okay, so that's how we use the REO rule. We look at which atom is being deprotonated, and if it's more electronegative, then that is going to be the stronger acid. And of course, we can confirm that using the pKa table. The pKa of butane is 50 for alkane, and the pKa of an alcohol is 16. And sure enough, 16 is way, way, way less than 50. So that means that the alcohol, in agreement with the pKa table, is much more acidic than the alkane, butane. All right, great. Now, this said same row. What if they're in the same column? And I won't ask you to compare diagonally. So it's either going to be in the same row or in the same column. But let's see what happens if they're in the same column. Okay, when we're in the same column, we want to go down. Larger size equals more acidic. And this makes sense. An atom with a larger atomic radius is going to be better able to tolerate the electrons of a negative charge, because there's more room for all those electrons to spread out. So let's take oxygen versus sulfur. Let's compare propanol with propane thiol. If we treat both of these guys with a base, You're going to deprotonate both of them. And we're going to end up with the propoxide anion. And the sulfide anion. And since sulfur is lower than oxygen, it's larger than oxygen, and therefore it is more stable conjugate base. And therefore it's a stronger acid. Okay, and again, we can compare the pKa's to confirm that our answers are right. The pK of an alcohol is 16, and the pK of a thiol is 13. You can look at the pK table to confirm that. And indeed, 13 is lower than 16, so that is in agreement with our REO method. Okay, so that's A for REO. If you're comparing atoms, that's the most important factor for deciding acidity, and more electronegative is more acidic, and larger is more acidic. All right, let's move on to R, resonance. That's the R of REO. Okay. Let's compare ethanol versus phenol. Let's treat both of these guys with a base. And what you'll see is that they're both going to lead to a negative charge on oxygen. So we won't be able to use the atom effect to decide the winner. The atom effect won't help us here because the negative charge is on oxygen in both cases, but we can use the resonance, which is the R in REO, to determine who's more stable. And take a look at the bottom example, can participate in resonance. There's multiple resonance forms available. We've got lone pair next to pi, and we can draw a bunch of resonance structures, stabilizing or delocalizing that negative charge. So there's a negative charge there. We can do another lone pair next to pi and move the negative charge down here. There's actually quite a bit of resonance going on here. Draw another resonance structure, several resonance structures available to this molecule. Okay. And so because we have resonance, that is going to stabilize the conjugate base. So that means the bottom option is more stable. Stronger acid. Okay. The more we can stabilize our conjugate base, the stronger the starting material is going to be as an acid. The more likely it is to give up its proton, because when it gives up that proton, it can deal with the consequences of that. And say, listen, I lost my proton, I lost my love, but I can do resonance and keep myself busy till he comes back. Or, compare the top case, I lost my proton and I can do nothing about it. My electrons are stuck here on this oxygen. I can't produce any resonance structures. I am higher in energy. I'm less stable in this situation. And we can look at the pKa table to confirm. The pKa of an alcohol is 16. And what about this bottom molecule? If you look at the pKa table, there's actually a special entry for it. Phenol, special type of alcohol, and it has pKa of 10. And indeed, 10 is lower than 16. So that's a major difference in pKa just because of resonance. So notice though that like the difference of 6 is actually, it's a logarithmic scale. So that's a difference of 1,000,000. 10 to the power of 6 is actually the acidity difference. So that means phenol is 1,000,000 times more acidic than ethanol. And it's all due to the resonance effect. All right, let's move on to I, which is standing for induction. Induction has to do with electron density being pulled through sigma bonds. Let's take a look at an example of this. So an example would be acetic acid. Treat that with a base, and we get acetate anion. Compare that with trichloroacetic acid. It has 3 chlorines on the left carbon there. So in both cases, we have a negative charge on oxygen, so the atom rule is not going to help us here. In both cases, we have resonance structures available. We can always draw resonance structure lone pair next to pi in both of these cases. So resonance is not going to help us break the tie, but rather induction will help us break the tie. Notice that we have these electronegative chlorine atoms in the bottom molecule, but we have only hydrogen atoms in the top molecule. Well, the electronegative chlorine atoms will help pull the negative charge inductively towards each of the chlorines, helping to stabilize the corresponding anion by spreading the charge out, by sucking electron density through the sigma bond network. This is called induction. And so what that means is that the bottom case is more stable. We've got electronegative atoms nearby that can suck that negative charge and spread it throughout the molecule. So more stable Cls help spread negative charge. And this is really nice that we can use the ARIA method on this, because if you use the pKa table, you'd be at a loss to kind of determine the different acidities of these guys. They're both carboxylic acids, and when you look at the pKa table, you'll see that there's only one entry for carboxylic acid, it's 5. So how are you going to determine? You can't use our pKa table to figure out which one of these is more acidic, but if you actually look up or measure the pKa's of these compounds, the top compound, acetic acid, has a pKa of 5. The bottom compound, trichloroacetic acid, has a pKa of 1. So that is indeed lower pKa, and so you can see the inductive effect is quite dramatic. That's a difference of 4 pKa units, which is 10 to the 4, which is going to be 10,000 times more acidic than acetic acid. Okay. That's the inductive effect. And finally, orbital, the O of REO. The orbital effect says that the more S character you have, the more stable. And this is the last case tiebreaker. Let's take an example here. Here we have propene versus propyne. Treating both of these with a base, the propene will become the propenyl anion, so negative charge over here. And the propyne will become the propynyl anion, negative charge here. And so we can't use the atom to differentiate these two because they both have a negative charge on carbon, so atoms is equal. We can't use resonance. Neither of these guys has resonance structures available. You can't draw any resonance structures for this lone pair. Remember, lone pair next to pi is a valid resonance scenario, but lone pair on pi is not a valid resonance scenario, so neither of these guys have resonance available to them. There's no induction here, there's no electronegative atoms, but we can use the orbital distinction to help break the tie. And so what we'll find is that the first case, the negative charge is contained within an sp2 orbital, because the hybridization of that carbon is sp2. And in the bottom case, the negative charge is in an sp orbital, because the carbon that it's on is sp hybridized. And the rule says that the more s character you have, the more stable you are. And that's because the s orbital is held more closely. The more s character you have, the more closely the negative charge is being held to the nucleus. The nucleus has a positive charge, so you want to hold the negative charge close to the positively charged nucleus. So sp is more stable than sp2, which is more stable than sp3 when it comes to a negative charge. So this is more stable. So our alkyne is the stronger acid, and indeed you can look up the pKa table and find that alkene has a pKa of 43, and alkyne has a pKa of 25. 25 is quite a bit more low than 43, so the orbital effect is the explanation for that. The alkyne is more acidic than the alkene because of the orbital effect. All right, awesome. So that is the REO method, and we'll do examples of practicing deciding acid and base, or deciding acid strength using the REO method in class. Now I want to change gears because we're still really talking about general chemistry in a sense. We're talking about acids and bases, but I want to now transition. And what I found is that this transition from acid and base reaction to organic reaction is a pretty natural transition. I think you're going to make it make sense. So I want to just recall one important concept, and that is reaction mechanisms. And then we're going to start to segue into our sort of what I think is the second half of this class is right now we've mostly been talking about structure and bonding and different things like conjugation and aromaticity, but now we're really going to start talking about chemical reactions, and pretty soon we're going to learn how to build molecules, which is awesome. That's my favorite part of organic chemistry. If I'm being honest, this second part of the class is awesome. Okay, so first I want to recall our idea of the reaction mechanism, which is using the curved arrows. So let's just take a look at an example of a reaction mechanism for an acid-base reaction. So if we have hydrochloric acid, I kind of drew it backwards, ClH. You'll see why in a second. And if we react hydrochloric acid with hydroxide ion, an acid-base reaction can occur. And we can draw a reaction mechanism to show that. If you remember, the lone pair of the base grabs the proton of the acid and then breaks the sigma bond between the proton and the conjugate base. That's going to lead us to get the chloride ion plus our conjugate acid, which is H2O. So that's a reaction mechanism. And what you'll notice happens here is that the negative charge of the hydroxide is attracted to the delta positive of the ClH bond. You notice that this is a polar covalent bond. The H is more electropositive than chlorine, so we can draw these little partial charges. This chlorine has a delta minus, and the H has a delta plus. And so if we drew our dipole arrow, it would look like this. And so the polarization of the HCl is really important. It's what guides the reaction mechanism. It's what tells the OH minus to grab the H and not the Cl. The OH minus has a negative charge, so its electrons are attracted to the delta plus atom, which is the H. Now keep that in mind. That is going to be the most important concept that is going to guide us through all the reactions in organic chemistry. It turns out that almost every reaction in organic chemistry involves electrons attacking a partially positive position. If you can just remember that negative likes positive, everything is going to seem easy in this class. So just two comments before we get into it. Segueing away from acids and bases into our organic version of acids and bases. And that is that all arrows start from electrons. And that means it's either going to be a lone pair or a bond, because electrons are represented in our bond line drawings as either lone pairs or bonds. Because what's a bond? A bond is just electrons too. So all arrows are going to originate from a lone pair or bond. That means if you have an atom that doesn't have a lone pair on it, there's never going to be an arrow originating from that atom. It can only start at a lone pair or a bond. And the second comment I want to make, almost all OChem reactions involve electron attack. We're going to see that word a lot, attack. That means the arrow pointing to positive or partially positive charge. We're going to see this a lot where we have electrons attacking something that's partially positive. And we need to define two terms. And these two terms are sort of related to acid and base, but they're a little bit different. So the terms are nucleophile and electrophile. They're more generic than acid and base. Okay, nucleophiles and electrophiles. These are the main players in every OChem reaction. They're so important. So let's define nucleophile. Nucleophile means nucleus loving. It's anything that likes a nucleus. What is the charge of a nucleus? It's positively charged, because what's inside the nucleus? Protons and neutrons. No electrons inside the nucleus. So nucleophiles, they are going to be electron pair donors. So nucleophiles give a pair of electrons. And so they're attracted to positive charge since they're giving negative charge. So generic abbreviation for a nucleophile is going to be Nu with a lone pair on it, because generally nucleophiles have a lone pair. Sometimes you'll see a negative charge on the nucleophile, but not all nucleophiles need to be negatively charged. They just need to have a source of electrons to give, either a bond or usually a lone pair. A electrophile complements the nucleophile perfectly because it's electron loving. It accepts a pair of electrons. And this is sometimes generic abbreviation as E+ for electrophile. E+. So you can kind of see this is similar to the acid and base idea. Electrophile, instead of accepting a proton, it's accepting a pair of electrons. And a nucleophile, instead of giving a proton, it's giving a pair of electrons. So the whole concept of acids and bases, donors and acceptors, the analogy is now moving towards organic chemistry, where we're talking about two new terms, not acid and base, but nucleophile and electrophile. So if you look at the example above, hydroxide is acting as a nucleophile because it's giving a pair of electrons, versus HCl is acting as an electrophile because it's the target of those electrons. So each molecule is either going to be a nucleophile or an electrophile, generally speaking, in an organic reaction. And you can also have things like the electrophilic center. So like a particular atom inside of an electrophile can be the most electrophilic atom, and you can call that the electrophilic center. So how do we identify nucleophile and electrophile? That's going to be our next goal. Because if you want to figure out what happens in an organic reaction, you need to be able to figure out who is your nucleophile and who is your electrophile. That will allow you to draw a mechanism, and once you draw the mechanism, you can figure out the products. So to figure out the nucleophile, you want to look for a few clues. The nucleophile is either negatively charged or partially negatively charged, usually. There's a few exceptions, but you want to look for that negative or partial negative charge. The nucleophile usually has one lone pair minimum. And if it doesn't have a lone pair, it'll have pi electrons of an alkene or alkyne. Pi electrons, meaning the double or triple bonds, are usually nucleophilic. Not always, but usually. To help spot the electrophile, you'll want to look for a positive or partially positive charge. That's your biggest hint. Another thing to look for is less than a full octet. So if you have less than 8 electrons, that's obviously going to be hungry for more electrons, so that makes it a good electrophile. And then you might also want to keep your eye out for a weak bond. A weak bond is a bond that can sometimes break. And if a bond breaks, that causes an electron deficiency, making something electrophilic. So just look for that weak bond. We'll talk about what is a weak bond. Let me just give you some more concrete rules to help you decide between nucleophiles and electrophiles. So those are kind of generic, but here are more rules. Okay, all lone pairs on the following atoms are nucleophilic: carbon, oxygen, nitrogen, sulfur, phosphorus are nucleophilic. And that is regardless if it's negative or even if it's neutral. Okay, so lone pairs on those atoms are making that substance a nucleophile. all lone pairs, I'm going to abbreviate that LP, on halogen atoms like fluorine, chlorine, bromine, and iodine are nucleophilic, but only if negative. Meaning a neutral chlorine, it has lone pairs, but it is not nucleophilic. Only negatively charged chloride, bromide, iodide would be considered nucleophilic. Okay, so those are some tips to help you spot some nucleophiles. All carbonyls, I don't know if I've mentioned what a carbonyl is. I think I have. Carbonyl is just a name for any compound with a CO double bond. It could be a ketone, an aldehyde, an ester, an amide. The CO double bond are electrophilic at carbon. Meaning they are electrophilic right here on this carbon of the CO double bond. Anything connected to a neutral halogen is electrophilic. And anything with less than 8 electrons is electrophilic. Okay, so let's do an example. I'm going to write out a bunch of molecules, and then you're going to pause the video and try and decide which one of these molecules is nucleophilic and which one's electrophilic. Okay. Just write them out now. Okay. All right, pause the video if you want to try and figure out which one of these is a nucleophile. So go ahead and circle all of the molecules that are nucleophiles, and anything you don't circle, everything else is an electrophile. Okay, so all of these molecules here are either nucleophiles or electrophiles. Okay, pause the video if you want to try this on your own. Otherwise, I'm going to go through the answers right now. Okay, so let's go ahead and circle our nucleophile. Let's take a look at the first molecule. First molecule is negatively charged, so that is a huge hint that we have a nucleophile. Almost everything that's negatively charged is going to be a nucleophile, and sure enough, we do have lone pairs on this oxygen. And rule number 1 says that all lone pairs on oxygen are nucleophilic, even if it's neutral, but definitely if it's negative. So we are going to go ahead and circle this as a nucleophile. Second compound here, we have a halogen. The halogen has lone pairs. But halogen lone pairs are only nucleophilic if it is a negatively charged halogen. This is a neutral halogen. That is not a nucleophilic substance. In fact, anything connected to a neutral halogen is electrophilic. So this is an electrophile because we have things connected to a neutral halogen. That is not a nucleophile. Next up, we have carbonyl. All carbonyls are electrophilic at carbon. So the carbonyl, the aldehyde there, is not a nucleophile. It is an electrophile. Next up, we have ammonia. Ammonia is a neutral molecule. It has a lone pair on nitrogen, but if we see here that all lone pairs on nitrogen are nucleophilic, even if they're neutral, that means this is a nucleophile. Go ahead and circle that. BH3, borane. Boron has less than 8 electrons. It has 6 electrons in this case. It's one of our octet violators. So that means it is an electrophile, so we're not going to circle that. I-, it's a negatively charged halogen. It says right here that all lone pairs on iodine are nucleophilic, but only if negative, and this is negative. So that means the lone pairs on this iodine are nucleophilic, which makes the whole iodide a nucleophile itself. Okay. Next up, we have the alkene. If you remember, pi bonds are weakly nucleophilic. We saw that on the previous page here. It wasn't part of our more rules, but it said here that pi electrons of alkene or alkyne, those meet the definition of a nucleophile. So we'll go ahead and circle that since there's nothing really else to say about it. We have a thiol. There is lone pairs on the sulfur. We know that lone pairs on sulfur are nucleophilic, whether negative or neutral. In this case, the sulfur is neutral. No charge shown, but it is still nucleophilic. So we'll go ahead and circle that. HCl, we got something, anything connected to a neutral halogen, that's an electrophile. We're not going to circle that. And II, again, we have anything connected to a neutral halogen, that's electrophilic, so that's also an electrophile. Okay. So hopefully you'll get good at identifying nucleophiles and electrophiles. That's the first step to becoming an organic chemist, is to be able to look at a molecule and recognize, does this fit into the category of nucleophile or does it fit into the category of electrophile? Now, you may be wondering, and I had a very interesting question. I had this idea. What happens if you put a nucleophile substance and an electrophile substance together in the same molecule? What happens? Well, it turns out that that molecule will self-destruct. So don't do that. Okay? You do not want to put a nucleophile and an electrophile in the same molecule. We'll take a look at some cool examples of that later in this class. But at this part of the stage of the game, it's either going to be a nucleophile or an electrophile. You won't have both qualities within the same molecule. That would be bad. Okay. It's going to react with itself if you do that. One thing I want to just talk about, and we're going to wrap up this lesson, I know it's been a long lesson, is the carbonyl. To me, the carbonyl is the most interesting because if you look at it, there's qualities of both nucleophile and electrophile in it. We've got lone pairs on oxygen. Wait a minute. I thought lone pairs on oxygen are nucleophilic, even if they're neutral. So why didn't we circle that molecule? We also have got a pi bond. I thought pi bonds were nucleophilic. There's two things telling me this compound's a nucleophile, yet you're not circling this. You're telling me it's an electrophile. Let's take a closer look at that, and then we're going to wrap it up. So I'll just say this. Sometimes molecules have both nucleophilic and electrophilic character. Or I'll say properties. In this case, one property always predominates. So let's take a look at an example. Let's take acetone. So if we take a look at acetone, we've got two properties that tell us it's a nucleophile. We have got lone pair on O. That is nucleophilic. We've also got a pi bond. That is nucleophilic. However, we can also draw a resonance structure for our carbonyl compound. If we move electrons up onto oxygen, polar pi bond, we can get a resonance structure. It's not a major resonance structure, but it's a resonance structure nonetheless that looks like this. And if you look in that resonance structure, you'll see we have an atom with less than 8 electrons. It's also a positive charge. So positive charge, octet not satisfied. That is electrophilic. Okay, so just to recap, in acetone, we have lone pairs that are nucleophilic. We have a pi bond that's nucleophilic. And then we have a resonance structure, even though it's not a very major resonance structure, that has a positive charge and an unsatisfied octet. And that is an electrophilic quality. So how can we determine who predominates? Do the two nucleophilic qualities predominate? Does the one electrophilic quality predominate? If you ask me with no experience, I would say that 2 beats 1 any day. This substance should be a nucleophile. However, we know from experiment that it is predominantly an electrophile. Is predominantly Only way to know this is by doing an experiment. There's no way that you can predict. There's no REO rules or anything like that for nucleophile and electrophile. So if you have competing factors, nucleophilic factors and electrophilic factors, the only way to tell the difference is use it in a reaction and see what role it plays. Only way to know this is to test it out. And sure enough, chemists have tested carbonyl compounds again and again and again and again and again, and they find that they tend to behave more like electrophiles than they do nucleophiles. Now, that's not always 100% the case. There are some situations where carbonyls act like nucleophiles, and we'll even look at some examples of that. But 99.99% of the time, the carbonyls are going to be electrophiles, and that we only know that from experiment. You would not predict it just by looking at the individual properties. Okay, let's go ahead and stop right there. And starting in the next lesson, we're going to learn our first organic chemical reaction, which is very similar to an acid-base reaction. It's called the SN2 reaction. We'll learn about that next time.